So let's maybe briefly review what we did the last two times. So we have the setting was we had this group G, which is countable, and then we also have a measure mu. Mu is a probability measure on G, and we also know that G is acting on some hyperbolic space. Okay, so this is delta hyperbolic, and our standing assumption is that the action is non-elementary with respect to this measure mu. So it's a non-elementary, and what that means is that well, first of all, if you look at the support of the measure, so that's some kind of a subset of the group, and you look at the semi-group it generates. So you're not allowed to take inverses, just compositions of elements in the support. So this is the semi-group support. Then this contains a loxodromic. That's one condition, and the other is that well, I guess equivalently, the whole group generated by the support doesn't have a finite orbit in the Gromov boundary. No finite orbit. Finite orbit in. Okay, so that's just what it means to be non-elementary. Okay, and then what one does in random walks is that you look at the so first of all you look at the infinite product of the copies of the group, and because a random walk is going to be induced by picking a sequence of elements according to this measure. So this product here is equipped with the product measure. So there's the product measure. And then, given a sequence like this, you compose, right? So this is how you build your path. So this goes to the space of paths, which is also, as a set, it's also the same thing, but it will have a different measure. So this is the set of I like to think of it as actually as 1 cross g to the z greater than 0. In other words, this is the set of sequences that start with 1, and then it's omega 1, omega 2, and so on. And this map is given by taking g1, g2, and so on, mapping it to 1, g1, g1, g2, etc. Okay, that's the function. And then you push forward this measure, product measure. You push it forward over here. So P is the push forward measure. On omega. Okay, so that's the probability measure that we have on the space of these paths. These are called sample paths. And as we saw in the little video that I showed, that if you let's say x is a hyperbolic plane, you start at some point. So we're really interested in projecting to x. So we're really interested in considering the sequence omega n x0. You apply omega n, the element of this path here, omega n x0. We translate the base point by omega n, and so that gives us a sequence in this hyperbolic space. And then we were interested in considering what happens to that sequence. And in the videos, we saw that this gives some kind of a path that tends to converge to a point in the Gromov boundary. Okay, and that was the theorem that I sort of outlined last week. So this is due to Mar and Tiozzo. That under these assumptions of non-elementary, so for almost all, so with the exceptional set has measure 0, but for almost all sample paths omega n, we have omega n x0 converges to some point in the boundary for some lambda in boundary. Of course, different paths will converge to different points in the boundary, but almost all of them converge. Okay, and today I'd like to talk about the drift. Okay. So, yeah, maybe one more thing before. I should have also mentioned this. This might come up a little bit later, but there is a notion of, as a consequence of this, we can talk about the hitting measure. So we have a function that goes from omega to the boundary of x, and it's defined almost everywhere. Which it sends you take one of these paths omega n and you send it to the limit of omega n x0. Right? So this is now well defined away from a set of measure 0. And you can take this measure that you have on P and you can push it to the boundary, and that's the hitting measure. Right? So you get the hitting measure nu on boundary x. And this measure is easily seen to be one of the stationary measures that we talked about last week. So it's a stationary measure. And that means that if I take a measure of any measurable set, u in the boundary, that's going to be equal to the sum. It's the average kind of the, I take mu of g, nu of g inverse u, overall g and g. Right, they're just expressing the fact that the probability of going from series x0, the probability of your random walk ending up here is you consider the first step. The first step is given by this element g. So let's say you make the step g, and then you're wondering what is the probability of going from this point to u. Well, because everything is invariant under translations, that's the same as the probability of going from x0 to g inverse of u. And then you kind of weigh it by the probability that the first step is g. So it's some sort of average like this. So it's a stationary measure, and also and we show that every stationary measure is non-atomic. So it's only non-atomic. In fact, with a little more work, one can show that that in this situation there is only one stationary measure, and it's the hitting measure. But we won't need that. That requires a little bit more work. Okay, so today I want to talk about the drift and maybe some applications of the drift to geometric group theory. But what is the drift? So what you want to consider is, you have one of these sample paths omega n, and you look at the distance. How quickly are you moving away from x0? So you look at the distance between x0 and omega n x0. So after n steps, you're somewhere in your space. You measure the distance. You divide by n. Okay, and so you'd like to know that this maybe converges to some positive number. That would be good. That would mean that you're moving away with some non-zero speed. Okay, so the theorem, again by Martin Tielsa, there are really two parts. So the first step is that there is some constant, some positive constant eta, so that for almost all omega, right, for almost all sample paths, if I look at my so this picture is really induced by one of these omegas, right? I look at how quickly it's going off to infinity. Well, it's with speed at least eta. Okay, so for almost all omega, if I look at the lim inf of this divided by n, as n goes to infinity, that's at least this number, eta. It's the same eta for all paths. It's not just that it's positive on all paths, but in fact it's uniformly away from 0. Moreover, so there is now a mild condition, mild additional. So this is without anything else, just our standard assumptions. But if mu has what's called a finite first moment, which is true kind of for most random walks of interest, finite first moment, then in fact this limit exists and it's positive. So then there exists some say eta prime positive, so that for almost all omega, you don't need inf here. Lim then goes to infinity of the distance from x0. So they actually go to infinity with exactly the same speed. Okay, that's maybe surprising. Okay, so now so that's what I'd like to maybe do today, and then there are some applications The first one is this is a theorem of Thomas Hettel. And in fact, there was an independent argument that doesn't use random walks, but I guess I'll feature here Hettel's approach. So this is due to Bader and Fuhrman. So the theorem is that if gamma is a higher rank lattice, so it's a lattice in a rank greater than 1, let's say simple Lie group. I mean, you can put some other words here, but simple Lie group. Then every action of gamma on a delta hyperbolic space is elementary. Okay, there are no interesting actions of groups like SL3Z, let's say. If SL3Z acts on a hyperbolic space, then the action is elementary. That is, its orbits are either bounded, or maybe there is a finite orbit on the boundary. So for groups like SL and Z, this was actually done earlier, maybe on the order of 15 or so years ago by Jason Manning. And maybe there were some other cases that were done by other people. But in this generality, this is very recent. I think Hettel is maybe a year ago. And Bader-Fuhrman is not even written up yet. So this is very recent. And I have to say, I don't understand all the, I mean, it's kind of a longish paper, but I do understand the main idea. Okay, the main idea is to use this drift business. So you, okay, maybe I'll just go over here and say a few words about this. So one knows a lot about the analog of random walk on symmetric spaces, and the right thing is to look at Brownian motion, which is random walk is some kind of a discrete version of Brownian motion. But people know a lot about Brownian motion on symmetric spaces, and so what you do is so the idea for Hettel is to find carefully. So this is the hard part. I mean, to find this carefully a probability measure mu on gamma on this lattice that in some sense approximates the Brownian motion. Gamma sits inside some symmetric space. You think of it as being it's acting on some symmetric space, and symmetric space comes with a Brownian motion that one understands quite well. So then the idea is to use to approximate that by some kind of random walk on the group gamma, sort of discretize this Brownian motion and make it a random walk on gamma, so that the drift on gamma is 0. Okay, so you'll be going to infinity, but very slowly, sublinearly. And then, but then the map, but gamma to to the isometry group of X is this action. So or maybe I'll just say the orbit map. This is the orbit map. If gamma is also acting on this delta hyperbolic space X, the orbit map is Lipschitz. And so the drift cannot get bigger. The drift will also be 0. So the drift on X is 0, and that's a contradiction to the Martiozzo theorem. Okay. Okay, and the second application is this genericity business. So this is still not quite well understood, but you want to say things like Pseudo-Nassov. So pseudonosovs are generic elements of.
So you mean if you assume the action is non-elementary, then you carefully find the probability measure non-elementary.
Well, the non-elementary comes in Martiozzo theorem. So you have to, in Martiozzo theorem, the standing assumption was that the action is non-elementary. So if the action of gamma on X is elementary, then there's no contradiction, and that's what must happen.
Right.
If you had a non-elementary action, in fact, this measure here is going to have full support. Every element of gamma is going to have non-zero probability. So there is no problem with this subtlety in the definition of non-elementary. It's just that if you have a non-elementary action of gamma on X, then this, when you equip it with that probability measure,
right,
it'll be a non-elementary action in the sense of Martiozzo.
And then you get a contradiction.
And then that's a contradiction. Of mapping class groups. And then, of course, there are similar statements you can make. It's like I can say fully reducible. This is because this is my favorite thing. Reducible elements are generic elements of out of n. You can say, I don't know. Rank, if you like rags, you can say rank 1 elements are generic in the automorphism groups of. Well, you have to make sure that the rag is not reducible. It shouldn't be a product or something. It should contain, as long as they contain rank 1 elements, then they're generic. Or if you have a hyperbolic group, elements of infinite order are generic, right? You might have torsion, and so so there are things like this you can say, and what this really means is that if you run a random walk, then after n steps, you can ask yourself, what's the probability that I have a pseudonosov? And the answer is that probability converges to 1. So so with overwhelming probability, as you run the random walk, your element is going to be, nth element is going to be pseudonosov. And so the actual theorem is that in the situation of, so again, this is Martiozzo, under our standard assumptions. So with standard assumptions, there exists some L positive, so that the probability that the translation length, so tau is my translation length here. Maybe I should remind you what translation length is, of omega n. Translation length of omega n is less than or equal than Ln. This goes to 0 as n goes to infinity. Okay, so to translate, this is the asymptotic translation length. So tau of any element G. So G is a hyperbolic isometry of a hyperbolic space. And then tau of G, you take the distance between your base point and G to the n of the base point, and you divide by n, right? And you take the limit as n goes to infinity. So the limit always exists, and is independent of the choice of x0. And so this is going to be positive if and only if G is loxodromic. Okay, and so this is saying that, for certain small L should be thought of as a small number, right? But the probability that at the nth step, the translation length is less than this number times n is going to 0. So chances are the translation length is bigger than this, and in particular, it's positive. Okay. So that's sort of the precise statement in which pseudonosovs are generic. And that somehow confirms this is what people always did, right? You take some generating set of the mapping class group and you start randomly composing, and you have to be extremely unlucky that if you actually don't get a pseudonosov after 5 or 6 compositions or something. Okay, so that's the program.
On the curve complex.
On the curve complex, yes. So that's right. So here you would be looking at the action of the mapping class group on the curve complex, And for this, you'd be looking at the out Fn action on the complex of free factors. Okay, so, all right, any questions?
Do they also get control over the distribution of the translation length, like how far it's spread around their average?
Not in this paper. I don't know if they thought about it or not. No, they don't discuss it in this paper. But those are good questions, yes. Although I think, my guess is that, what would you expect? I think you would expect, just like in the drift case, you would expect that there's a sharp, if you divide by n, tau of omega n divided by n, that should converge to some fixed constant that's independent of the sample path almost everywhere. Okay, so so the arguments are actually going to be pretty geometric, and they have to do with estimating, what's the likelihood of your n and walk hitting some distant half space and stuff like this. So we'll go through those kinds of arguments, but there is a theorem in ergodic theory that this relies on, and maybe I'll do that first to get analysis out of the way. I won't prove it. I'll just state it. Right? We are consumers of analysis. Okay, so this is called Kingman's subadditive ergodic theorem. Okay, so it's like this. So you have so omega p is a probability space, and you can guess what we're going to apply it to from the notation probably. And u is going to be a measure preserving transformation. And then we'll have a sequence of functions from omega to r. These are all going to be measurable functions. So this is from n equals 1, 2, and so on. These are measurable. And not only that, but I also want them to be integrable. That is, the integral should be finite. Or, I guess it's enough to just assume that W1 is integrable from the next condition. Okay, so what is subadditive here? So subadditive just means that Wn, that's the main condition here, Wn plus m is less than or equal than Wn plus Wm composed with u. And maybe I'm not sure if this is really required, but certainly all our functions are going to be non-negative. I don't want to have to take absolute value or whatever. Okay, so that's what subadditive means, and it should be pretty clear what how we're going to use it in a second. Let me just finish stating it. Okay, then there exists a u invariant function, integrable function. It's w infinity, and it goes from omega to r plus. So that you take Wn over n, this converges to W infinity, so it converges, not by some, after some subsequence or lim inf or whatnot. It just converges, and this is in L1, or, and also pointwise almost everywhere. Okay? That's the theorem. Now, okay, so now I'll give you a quick example in a second. But let me point out that if, and this will be true in our situation too, that if so there is a natural circumstance when you can actually deduce this W infinity is constant, right? So you can see that the relevance to drift, because this Wn might be the distance between the base point and Wn of x0, right? And then we're dividing by n, and we like to know that this converges to some constant. That's our goal. So we should be able to somehow, in addition, deduce that W infinity is constant. But what we know is that it's U invariant, okay? And when you have a situation like this, you have a function on some probability measure space, and it's invariant under some U, then what is it that you need to know to conclude that it's constant? Do you know? What?
Transitivity.
No, it's ergodic. If U is ergodic, then so what does it mean to be ergodic, right? When is U ergodic? Well, one definition is to say that if you take any U invariant measurable subset, then its measure is going to be either 0 or 1. There's nothing in between. But another equivalent way of thinking is that any U invariant function, which could be the characteristic function of your set, for example, but it could be any function, any measurable function, then that function is constant almost everywhere. Right? So note that if U is also ergodic, then necessarily this W infinity is constant. Okay, so this is somewhat we'll be in business when we're in this situation, because we'll know that these functions that we'll cleverly cook up so that they're exactly what we're interested in here. This will converge to some constant function, and that's what we want to know. Okay. Okay, so let me now describe how we're going to use it. So omega we already know, and p, right? That's our space of paths, and p is the probability measure on the space of paths. Now, what is u? Okay, so u is basically the shift, although you kind of have to be careful how you define it. It's really the shift on that product space, and then there is some kind of induced map u on omega. Okay, so let me draw this big diagram. Let's see, where did I put it? Here. Okay, so here's the diagram. So this is the product space, and then we have this omega, and we have our function that I already described, right? That's the function that sends that's g1, g2. This goes to 1, g1, g1, g2, and so on. Okay, over here we have our shift map t. So maybe I'll just do it like this. Okay, so this g1, g2, that just goes to you erase the first element. So g2, g3. That's the usual shift, right? You just forget the first step, and you run your random walk just from the second step on. What happens here? So here I have a the same function that goes to omega, and then this is going to be the u. So what is in the picture? What does this mean? So we'll compute the formula in a second, but you have your random walk that kind of looks like this. Now I want to forget the first step, so I really want to start from this point, but I don't like to start from points that are not my base point. So what I really want to do is take this truncated path and then translate it to the origin. And that's the shift. Okay? So, so you define u so that this diagram commutes, right? So this is going to be 1, g2, g2, g3, and so on. And if you want directly in terms of the omegas, right? So it's omega 1, omega 2, and so on. This goes to you're forgetting omega 1, but you're composing. So it's omega 1 inverse, omega 2, omega 1 inverse, omega 3, and so on. Okay, that's really what u is. Okay, you forget the first step. If you didn't have omega 1 inverse, you would just be looking at omega 2, omega 3. That would be the usual shift. But you really want to start at the same base point, not at some other point. This point here is omega 1. So to start at the base point, you multiply on the left by omega 1 inverse, and that's this u. And you can check that this diagram commutes. So that this u should be really thought of as being the correct shift on the space of paths. Okay, now there's a famous theorem in probability that this t is ergodic. This is called the Bernoulli shift. Okay, this t is Bernoulli shift. This has nothing to do with groups. I could do this on any measure space, right? I could make the infinite product, and then I can make the shift, and this is always ergodic. It's ergodic. Okay. Now it follows just from the commutativity of this diagram that u is ergodic. So this implies that u is ergodic. Why? Well, this is just chasing the diagram. So if I had some invariant subset of omega whose measure is half, say, something between 0 and 1, then I could pull it back. Now, what's the measure when I pull it back? This is an exam question. What is the measure? This is how you define push forward, right? The measure is exactly the same. That's how this measure was defined. You take the pull back and you look at the measure here, and that's how you define the measure here. So it's still a half. And from the commutativity of the diagram, you see that it's t invariant. So that can't be, because t is ergodic. Okay, so this just implies that u is ergodic. And so, so we're all set for applying the applying this Kingman ergodic theorem. And so let me. Sorry, I'm all over the board, but I think it's important to have this on the board for this proposition. So this is kind of a sample application of Kingman's subadditive ergodic theorem. That if you have if gamma acts on x by isometries, and here x doesn't even have to be hyperbolic. X can be any metric space by isometries, and mu has finite first moment, then there exists some eta prime, which could be 0 for the, in this generality. We don't know that it's not 0, but so there is the drift is well defined. It doesn't depend on the sample path. There exists eta prime, so that for almost all omega n, the limit, the distance between x0 and omega n x0 divided by n exists, and exists and is equal to eta prime. Okay, so that's your speed, and it could be 0, but it's the same for all paths. Okay, so I have to tell you what finite first moment is and how to derive this from Kingman's subadditive ergodic theorem. Okay, so proof. So I'm going to define, what I need is these functions wn, right? Wn from, so to define wn from omega to r plus, r greater than or equal to 0. I want to define it to be, so I take this path omega, and what do? I take the nth step and I measure the distance from the order. So this is the distance from x0 to omega n x0, right? That's my function. And okay, so now there's some. How do you see this? How do you see? What is this? This is the triangle inequality, right? I have so here's my x0, and then I have wn of x0, and then a little later I have wn plus m of x0, and I'm applying the triangle. This is exactly the triangle inequality for this triangle, right? This is my function wn. This is my function wn plus m, and this is after shifting. I have to shift this, right, to put it back to x0. But this distance is equal to it's wm composed with u, because I'm shifting. Yeah. Maybe no. This should be. Did I say this right? Maybe this should be u to the. This should be u to the m. Sorry about this. You have to shift m times. You have to shift.
Not u to the n times.
n times. Yes. This is n. Yeah, you have to shift n times. Okay, but anyway, it's just a triangle inequality. And then the conclusion is exactly what you want. The Wn over n converges to W infinity, which is now we know is constant because U is ergodic. But there is one assumption I have to check, namely that W1 is integrable. If W1 is integrable, then from this inequality you get that they're all integrable, right, by induction. Okay, so what is W1? Well, that's exactly the finite first moment. Okay, that's the finite. The first moment is exactly the integral of W1. What this is saying is that W1. So this is saying that the expected size of the first step is finite. So finite first moment just means that the sum of mu of g, the distance from x0 to gx0, is finite. This is the expected size of the first step, right? If your first group element is g, then this is the size of the step, but then you have to average it over all group elements, and that's exactly the integral of W1. And so that does that. So you can see that this is under this mild assumption. For example, if you're thinking of a random walk that's generated by the measure supported on some finite generating set, then this is always true, right? This is some finite sum. Okay. So all right. So now I want to go and try to convince you that it's positive, that the drift is positive. And for that, we don't even need the first moment. This is just to say that the speed is constant over all paths. Okay. And we'll need a little fact from measure theory that I don't think I'll prove if I have time at the end, but which just seems unlikely at the moment, then I can prove it. But it's one of these things that's if you're taking an analysis exam, it could be there. So let me just state it, and then I think the rest is going to be more or less all little geometry, hyperbolic geometry. Okay, so we'll need the following lemma. So Z is a metric space, and I have a non-atomic probability measure. So you already know what this is going to be, right? So Z is going to be the boundary of the hyperbolic space, and mu is going to be the Hipping measure. And so we already know it's non-atomic. So it's an atomic probability measure. Okay, then for every epsilon, there is R, so that every R ball, every metric R ball in Z has measure less than epsilon. Yeah, so small diameter sets have small measure as long as there are no atoms. Okay. The proof is one page, but let's skip that. Okay, so let's now start talking about the geometry of hyperbolic space and relating it to the probability of what sample paths do. Okay, so there is a sequence of steps. Okay, so the first one. So I want to say that the walk is transient with respect to bounded sets. Okay, so what I mean by this is that if I look at the probability that So for every fixed b is some big number, say, I look at the probability of that the distance between x0 and omega I of x0 is less than this b for some.
Quick question. So for this limit, do we need properties of the metric space or not?
No.
No, it doesn't.
Any old metric space.
I see.
So this will be applied to the boundary, to Gromov boundary. So you actually know that it's certainly not proper, but it's maybe complete. But you don't need that.
I see.
Okay, so the probability that for some I greater than or equal to n goes to the probability that this goes to 0 as n goes to infinity. Okay, so you kind of have to pause and see what this means. But right, so n goes to infinity. N is some large number, and I'm looking at sample paths that at some point later, at some point after this step n, return into the ball radius b. Right, so that should be pretty unlikely, right? You're running random walk, b is some ball, but they should all be going to infinity. They shouldn't be coming back to some ball. So indeed, this is the claim. That it actually goes to 0 as n goes to infinity. Right? It's unlikely that at some large step you're going to be contained in some fixed ball. Okay, so what's the proof? Okay, so the proof is I look at the set omega n. This is going to be the set of paths such that the distance between x0 and omega I of x, so this is sort of the complement of that, is greater than b for all I greater than n, greater than or equal to n. Okay, so that's the complement of that set, and I'd like to know that this probability of this set goes to, or the measure of the set goes to 1. Okay, well, what I know is that omega 1 is contained in omega 2 and so on, right? This is an increasing sequence because n, when n increases, you have less conditions, right? And and what else do I know? What do I know about the union of all these? So this has full measure, has measure 1. Why? Well, because whenever you take a path that actually converges to a point in the Gromov boundary, then it will eventually leave this ball. And so that path will be contained in some omega n, right? If n is the last time it's contained in this ball, then that's it's going to be in all the subsequent omega n's. And so, but from measure theory, this implies that the measure of omega n converges to 1 as n goes to infinity. Right, that's just measure theory now. Some monotonical increasing union. Okay, so that's that. All right, so now we have to talk about half spaces and the probability of hitting a distant half space. That's probably the heart of the argument. Okay, so the situation is I have a point, maybe the base point, and I look at some geodesic that goes to infinity in x. This is a picture in x, and I take some large number L, and I look at the half space. So I measure off distance L here, and I look at the half space. So what I mean by this is you have the nearest point projection to the ray, and you look at all points that map to this segment under the nearest point projection. That's a half space, and then you have a complementary half space. There are points that project to this ray over here. Okay, so and then I take, so this is going to be my, I'll call this half space H0. Okay, this is the half space H0. This is the half space to this side, right? So these are points that project to this ray, as opposed to this first portion. And then I measure off another L. Okay, so I get another half space over here. That's also L. Okay, so the statement 2 is that the probability that omega n enters a distant half space goes to 0 as the distance goes to infinity. Okay, that's the claim. So here, if I want to say that if L is large, then the probability of even entering this, the random walk is going to do some crazy things here, but the probability that it ever enters this half space is as close to 0 as you like, as long as you make L big. Okay, so here's the logic. So this is the main trick somehow is to consider 2 of these half spaces. Right. The main thing, the relationship with so here's X, and if from the point of view of X, if I look at here's my geodesic ray, and I look at some distant half space, right? Here's the half space. That's what it looks like in hyperbolic space. There's a visual metric on the boundary of X, and the main thing is that the diameter of the closure of the half space is going to 0 with the distance. In fact, the diameter of the closure of, let's say this is my H, this is the half space H. I look at the diameter of the closure intersect boundary X. So this is going to be on the order of so there's some constant A that's bigger than 1, and they raise it to the power minus the distance between x0 and the half space. That's how the visual metric works. Although you don't have to exactly know this formula. So this A here is when you define the visual metric, you have to pick some constant greater than 1. There is some kind of this is sort of a complicated business. But anyway, all that matters here is that this diameter goes to 0 when the distance goes to infinity, right? So when the distance between x0 and h goes to infinity, then the diameter of this h bar intersect boundary x goes to 0. That's all you need to know here for this proof. Okay. Okay, so probability that, okay, so now I want to look at okay, so omega h1, this is going to be the set of paths that enter h1, right? So h1 is my second, this half space here. The set of paths that enter h1. They could leave later, I don't care, but at least once they have to enter h1. And then omega n h1, this is going to be the subset of omega h1 where n is the first time it enters. N is the first enter time. Okay? It might leave and then come back and so on, but look at the first one, the first time it enters, that's n. Okay, so what is the the proportion. So when L is large, the proportion of paths in omega n h1 that converge to a point in h0 bar is, okay, so you tell me. So if I'm, okay, so I wait n steps and I find myself inside this half space h1. So here I am. And I'm wondering what is the probability that my random walk will converge to some point in the closure of h0 bar. So this maybe I'll draw the picture, more suggestively like this. So here's, so here I am. Maybe I'll draw it in the middle. I'm going to apply some isometry so that the place where I am is in the middle. And then h0 bar is like this. So here's this part here is h0 bar, right? It's a distant sort of boundary. I'm deep inside this half space. So this is the picture, right? Here I am, and my half space is everything but a little bit over here. So what is the probability that I will actually, when I continue my random walk and I'll be converging somewhere with probability, with almost surely, what's the probability that I converge somewhere inside this h0 bar? Well, that's the lemma, right? What I'm missing here is some very small set, assuming this distance is large. If the distance is large, the diameter of this set is small, and so it's measured small. So that means that the proportion of paths that converge to a point in h0 bar is greater than 1 minus epsilon by the lemma. Right? I'm using the lemma to convert from so I know that if I have a set of a very small diameter, in other words, if the distance here is large enough, then the measure is small. So that means that my limit is going to be, with very large probability, it's going to be contained in h0 bar. Right? And this is true. So and epsilon here is some small number. I don't know, 0.1 if you want. There's some fixed small number. Okay, so and this is true for every n, right? This is true for every n, and this thing here is a disjoint union over all these, over all n. So it's a disjoint union of things, but there's some very large proportion of each of them that where the limit is in h0 bar. So that means that this is true for all of these, for omega h1, right? If I partition my set omega h1 into all these sets, and the large proportion of each set converges into here, then that means that the large proportion of this whole set also converges in there, right? So this is true. So proportion greater than 1 minus epsilon of paths in omega h1 also converge in h0 bar. Okay. But what is the proportion of all paths that converge to a point in h0 bar? So I'm standing at x0 and I'm wondering what's the probability that my path will actually converge to some point in h0 bar? Well, what do you think? This is now some distant half space. So by the same principle, right, the probability is going to be small, right? Because it's the measure. So this is now inverted, right? So the picture should now be drawn like this. This is x0, this is h0 bar over here. What is the probability that I will converge to some point over here? Well, it's the measure of this set, but the measure of that set is small because the diameter of the set is small, right? So proportion, okay, but yeah. So you conclude. So okay. So what you conclude is that 1 minus epsilon times the measure of omega h1 is less than epsilon. That's what it means, right? The proportion. This is the proportion of paths that converge to to h0 bar, but that whole thing is less than epsilon. And so that means that, right, so P of omega h1 is less than epsilon over 1 minus epsilon, and that's small. That's close to 0. So that means that my set, the set of paths that enter h1, that set has small measure. Okay, so that's sort of the trick, the trick of two hyperplanes. That's what, or two half spaces. That's what you have to remember here. Trick of two half spaces. And by the way, I think I don't. For instance, I don't know how to estimate the drift. This is what I said the first time, right? I give you some explicit random walk, and I ask you what estimate the drift. The trouble is that these are very non-explicit, especially the lemma, right? The lemma is. I didn't show you the proof, but it's very non-constructive. It just proceeds by contradiction. So you assume you can find these smaller and smaller sets with definite measure, and then you somehow intersect and you find an atom. But you don't, the dependence between epsilon and r in the lemma seems mysterious. And so, estimating what these functions are here, I mean, there's something is converging to 0, but you don't know how fast, and you don't know how to estimate anything. Okay. Okay, well, there's one also knows that in for instance, when the support of the measure is bounded, in the sense that when you project, you have this measure on the group, and you can project it by the orbit map to x. If the support is bounded, then you can actually do better. You can see that this function decays exponentially. The function of the what is the probability of hitting a half space whose distance is, say, L. Okay, then this the probability decays exponentially with this distance L. But you still don't know the explicit constants that go into it. Maybe I'll skip that argument, although it's not too hard, but I'm a little worried that we won't get to some of the highlight. Okay, so I don't know, are there questions? Is everybody with me, or? Okay, we now get to the kind of the key argument. How do you know that you're making progress? That you're moving away from the base point at some definite speed. That's somehow what we have to prove, right? And maybe if I was going to just summarize the proof in a couple of sentences, then I would say, well, first of all, we know that with large probability we're going to get very far from the base point. That was our point 1, right? The transience with respect to bounded sets. So if you wait long enough, you're certainly going to be far away. And then if you wait the same amount of time, you'll probably move away, about the same distance. But how do you know that you're not coming back to the base point? Well, that's because you can set up these half spaces, and you can see that it's very unlikely that you'll go back to where you started from because of these half spaces. So, okay, so that's sort of the idea. Okay, so to carry it out, what you really want to do is consider not every single step of the random walk, but you want to speed it up. You want to consider every 100th step or something, so that you don't get lost in the little details of the random walk. Okay, so you define the k-step walk. Okay, so the xi is just going to be omega ki x0, right? So the k could be 100, and I'm just looking at every 100th step. And I'm going to say that a segment between xi and xi plus 1 is r persistent, okay, where r is some constant. if the following picture holds. So I have xi over here, and I have xi plus 1 over here. So these are 2 points in hyperbolic space. I can draw a geodesic between them. I can measure off the distance r and draw my half space here. I can measure off distance r from the other point, and I can draw the half space. What I want to know is that the distance in between is at least r. And I want to know that all the subsequent points in my k-walk stay in this half space. Okay, so all xj greater than I are here in this half space. And all the preceding ones are in this half space. And all xj less than I are here. Okay? So the random walk does something in this, a k-step walk is in this half space from the beginning of time. X0 is somewhere here. And from the beginning of time, it's in this half space. And then from xi to xi plus 1, it makes this big hop. And then it stays in this half space. Okay? Then we'll say that, that this segment is R persistent. Okay? So this is a good kind of a walk because it's very clean, right? There's this big step that's cleanly cut off by these two distant half spaces. And there's no interference between the walk here and the walk here. This is how we know we're making progress. Okay. That's maybe the key notion here. Okay, so should we make a break? Is this a good time for a break? Maybe it is.
It's up to you.
Why not? Yeah, let's make 10 minutes.
10-minute break. Okay, so we'll have a 10-minute break.